Syzygy episode 45, biggest neutron star ever. And welcome back for another edition of the Syzygy podcast. Sitting opposite me at the table as ever, Emily Brunsden. Hi, Emily.
Good morning.
So today we've got a story about something quite big, I guess, for its kind. It's actually
yeah.
It's actually quite small in other ways. We're talking about the discovery of a big neutron star.
The biggest neutron star.
But the weird thing is that neutron stars, for stars, are quite small. And so wrapping your head around it is big, but it's small. We need to talk about neutron stars today. Emily, what's going on? Who's found what? Why? What? Who?
So this is the biggest neutron star that we have ever found. And what's really, really cool about it is it might well be the biggest neutron star we ever find.
Oh, right. Okay, so neutron stars have a limit.
Because there's a limit of how big they can be.
Ah, okay. So this could be like biggest one ever, and literally we're never going to find one bigger than this. All right, we're going to have to unpack that one. But first of all, who's done what?
So this was a paper that was submitted to Nature Astronomy. So we're still waiting, I think, on the publication of that. But it's really, really exciting because it puts together a whole lot of really, really amazing physics into one paper.
Can I just pull you up there for a second? Because, I mean, this is something which in academia we kind of, we're surrounded by researchers here at the University of York who just take this as a matter of course. But people listening out there in listener land might not completely understand. You just said that this has been submitted to Nature Astronomy, but we might have to wait for a while for publication. Hang on, is it published or not? Where is this? Where did you find this?
When
and what
I
happens
was
next?
reading this yesterday, which is, what are we up to today?
Today is the
23rd of September.
Tuesday,
As of the 23rd of September, it hadn't been published, but the press releases were out. The article has been, I suspect, reviewed because it's had corrections made on the online copy that you can see. So I suspect it's going to be pretty much any day now. I mean, this is the process of publication. You submit a paper, it goes to a referee, they give you some comments, suggestions, and basically say, is it good enough to publish? And then if it is, then it gets published. That process is very quick for big, exciting discovery things like Nature papers. Quite often with Nature itself, you don't actually hear about the article until it's fully published. But for, there's different journals, say the journals that I publish in, it can take a few months for this process. And for small journals, it can even take years.
It can take a really long time. Yeah. But the fact that there's been a press release and that they're talking about this to the outside world says there's no danger here. This is publishable work. It'll appear in Nature any day now.
I think
Don't
so,
worry
yeah.
about it. Okay. But, if you don't really care about that, let's get on to the actual news, which is big honker neutron star.
Yes.
So who was this?
So this is a big collaboration of different people, but it's been led by Cromartie from the University of Virginia. Mm-hmm. And they've published this result. So they've got a millisecond pulsar, which is up to basically near the theoretical limit of mass that we can have.
Right. Okay. So we're going to need to talk about a whole bunch of things here today. We're going to need to talk about neutron stars and pulsars. We're going to need to talk about the fact that these things even have limits. Like why is there a limit? Where do these things come from? How are they... Help us out, Emily. Where are we going to start?
Okay, well, let's start with the system itself. It's such a cool system to observe.
So what have we found?
So this is a system where we've got a neutron star and a white dwarf.
Right.
Okay.
So it's a binary system.
It's a binary system. So they're orbiting around each other. Now, a neutron star and a white dwarf are two very, very dense, compact remnants of stars after they've finished their lifetimes. A white dwarf is basically the end result of a kind of a low-ish mass star.
So when you say lowish, like let's take the sun as a reference because it's the nearest one we've got and we kind of think that's what a star is. So in relative terms to the sun?
Something up to about 8 times the mass of the sun.
Okay, right.
Yeah. So they'll end up as white dwarfs. So a sun will end up as a white dwarf. And then if you get an even bigger star than that, then it can end up as a neutron star.
And am I right in thinking that the sun is a relatively small star? So most stars are bigger than the sun? Is that would I be right in saying that?
No. Well, the sun's about halfway. It's not halfway in the terms of how big it can be, but it's about halfway in terms of population.
It's like the median.
Yeah, there's lots and lots of small stars, not very, very many
out there.
enormous stars out there. So even though the sun's below the average mass of a star, it's kind of in the middle of.
Some of them are really, really big and they kind of skew the stats. Okay.
Exactly. Yeah.
All right. So enough about that. We've got a white dwarf and a neutron star in a system.
Yep.
So do we need to have a bit of a chat about how the hell you get a white dwarf and a neutron star in a binary system? Where have these things come from? Can we sort of drill down into that?
Of course. So they're the end results of normal stars when they finish the ends of their lives. So at one point, they were just two ordinary stars that were in this binary system, one which happened to be bigger than 8 times the mass of the sun and one which was smaller.
So they would have started out in a binary system.
Probably. Yeah.
Right. Okay. Because in my mind, I'm imagining, and we can talk more about this, I'm imagining that in going from being an ordinary star to becoming a neutron star or a white dwarf, like that's a fairly violent process. Yeah?
It totally is.
Yeah. So I would have thought, maybe naively, that the violent end of one of those stars would have meant that if you were in a binary system, you maybe wouldn't be in a binary system anymore.
It's definitely possible, yeah.
Right.
So we do have other situations where you have two objects in a binary system that weren't born that way. They can capture other stars. But I think, and this is a little bit my own conjecture, I have to admit, but I think because this system is quite regular, so the orbit's reasonably circular, which does suggest that the stars formed together.
Right. So you're saying that the chances of forming a binary system this regular after the fact is fairly low.
Fairly low.
Right. Yeah. Okay. So how did we get here then? Let's sort of follow this one down. We've got a neutron star and a white dwarf.
Yep.
How did we get them?
Okay. So let's talk about the white dwarf first.
Okay.
So that's something like the sun. What happens is when the sun reaches the end of its life, it basically runs out of fuel.
Okay.
So if you think about all stars are this wonderful balance. You've got gravity, which is crushing them down together, and you've got something holding them up to stop them crushing down into nothing.
Gravity's always pulling inwards, and if there wasn't anything else, it would just keep going down towards the center. But something else is pushing out. So in the case of the sun, which is just a star doing its thing, what's pushing out?
That's light, photons. That's generated by the nuclear reactions that are happening in the core of the sun.
Okay.
So basically it's being held up by its own fusion processes.
Right.
And then when those fusion processes slow down and stop, then we need to think about what's going to happen. So gravity then takes over as the master, right? So gravity starts squeezing the star together. There's a lot of other processes that go on during this time. Lots of the outer layers, for example, of the star are shed off because it just can't hold on to them anymore.
Why do they get shed off? We're talking about gravity sort of pulling things down in towards the middle. Why are they getting lost outwards? Seems to be the wrong direction.
It is it is a little bit, but what happens when the star evolves is it becomes enormous. You think about this idea of a red giant.
Right.
These are very, very large stars.
Yeah, I remember you saying previously the Earth is going to get eaten at some point in the future, probably.
Exactly, yeah. So that happens, it's when the star's still fusing, but it's getting towards the end of its fusion. And so when it reaches the end and it starts to run out, it's so big that it can't hold on to that bigness anymore, those outer layers.
Okay. Meanwhile, down in the core, you've got lots of gravity pulling things in and you're fusing more and more things and bigger and heavier elements, desperately trying. I mean, this makes it sound like the star's trying to do something. It's not trying to do anything. It's the gravity pulling it in and causing more and more extreme environments that say, all right, I guess now we can fuse this into that. And eventually you run out of options. You run out of energetically favorable fusion reactions that can happen in the core of the star. You run out of fusion options. Then what?
So you're going to need something to hold up this core. And it turns out the core is mostly made of helium because that's what the star has been fusing to. And when you crush it down, all these kind of atoms in there, then there's one sort of quantum mechanics force that starts to kick in at really, really high densities. And it's something called electron degeneracy pressure.
Ah, yes. Now, I remember reading about this and learning about this when I was an undergrad in physics. The thing here is, if I remember correctly, electrons don't like being in the same state as other electrons. Electrons like to be separate, different things. And when you squeeze them together really, really hard, all the electrons around those atoms and things, squeeze them together really, really hard, they really don't like that. And they push back really, really hard. And that's the pressure that you're talking about. We're squeezing this stuff down. We've run out of that outward pressure from the photons, the radiation from the fusion, the energy from the fusion. And now we're reaching this point where quantum mechanics itself is saying, we can't squeeze down any further than this and have electrons. It's not going to work.
Exactly. So if you imagine electrons are negatively charged, so negative charges repel. So the first step to go through is basically this Coulomb repulsion. So those two negative charges don't like each other. We go through that step pretty quickly. Okay. Actually, it happens during fusion anyway.
And that's a very, very strong force in terms of forces, but gravity is really taking over at this point. So we whip on past that.
But that's an easy one to imagine. You can imagine the two charges repelling each other. This is kind of the next layer down where the actual electrons themselves don't want to be crushed together anymore, so they start opposing that motion.
Yeah, this is not an electrostatic effect. This is a quantum effect. Who cares about the charge? Electrons don't like it when they get too close together.
They definitely don't. But there is a limit to how much you can actually crush these electrons down together. And this limit is called Chandrasekhar limit.
Okay. What happens at the Chandrasekhar limit?
So basically the electrons don't have enough force to hold up the outer layers of a star. And this happens when the mass of that white dwarf, or that end of star, is about 1.44 times the mass of the sun.
Okay. So it's all, interestingly, quite around, we're sort of talking about stars around the mass of the sun, which is pure coincidence, but kind of interesting as well. Who was Chandrasekhar?
So Chandrasekhar was a really interesting Indian astrophysicist. He was incredibly intelligent. He was, the wonderful story that goes along with the Chandrasekhar limit is that he was about 20 years old and he was traveling on a ship. This was in the 1930s. He was traveling on a ship from India to the UK to visit Cambridge. And whilst he was on board, he was a bit bored, if you like.
As he would be, it's a long way.
Started doing some theoretical calculations, and there were some new calculations about how much you could basically compress gases, what happens if you keep going. Quantum mechanics was all new at this point, and in the 20s and 30s was the development of these new ideas. And he basically on pen and paper just calculated how much mass a particular object could hold up if it had this electron degeneracy pressure. And he came up with this number of 1.44. Wow.
And that's legit. It wasn't then shown to be, no, don't be silly. Of course there's a way around that. No, that's actually real.
It's really legit. What was interesting was at the time it wasn't super well accepted, not because people didn't believe him. Actually, quite a lot of people, really clever physicists, agreed that this was true. But there were a few big physicists like Arthur Eddington, who was he was really into understanding the theory of stars. But because he was such a giant in the field and he thought, well, I don't like this idea of a limit. Because if you have a limit, you can go past a limit. And what happens if you go past this limit?
We'd rather not think about that. Thanks very much.
So there was this, black holes were a theoretical concept. And he thought, well, maybe, he didn't like the idea of this.
Theoretically, we're not ready to go there yet. So let's just pretend this isn't happening.
So basically, because he was such a well-respected physicist, it took a while for these ideas to become mainstream.
Isn't that interesting that psychologically, I mean, it's probably much more complex than this, but psychologically, if you don't want to think about it, you can actually move the direction of scientific understanding and research away from an uncomfortable idea. I think it really shows that science is actually done by flawed human beings after all.
It is. There is a real human element. So it's a real shame that Chandrasekhar's work didn't get recognised, or at least not early on. Yeah. Later on, he won the Nobel Prize. Yeah. But he got that in 1983.
He really is one of the big names, but it took a while.
Had to wait, 50-something years.
Okay, so this is his limit, and it's awesome. And you can go beyond that. I mean, it's one of the interesting things in physics that you can come up with all sorts of we get to this point and this happens and you can't possibly go beyond that. Well, you can.
Of course you can.
Often there's something else that can then kick in, and you're talking about different interactions and different things that can happen at different energy levels. So you've got all this mass dragging down, pushing harder and harder, increasing the amount of energy that you've got in a small space, increasing the density, increasing the temperature, increasing the energy that you've got. And eventually you just sort of kick on past these thresholds of, well, you know what? At this energy, at this temperature, at this density, this new thing can happen. So what's the new thing that happens at the Chandrasekhar limit?
So, well, nobody tells stars how big they're allowed to be, right?
No,
So,
they just are.
They just are.
No one asks.
So if your star is bigger than about 8 solar masses, you crush through this electron degeneracy pressure limit, and you keep crushing down with the gravity that's being forced down into the core, and you end up in something called neutron degeneracy.
Okay, now hang on, because what you learn in first, second year quantum physics at university is that electrons, not just they don't like to be near each other, they won't. Like, this is a hard line. You cannot have two electrons in the same state. It's not possible. So something's happening when you're crossing that barrier to allow you to go further. What's that
Well,
thing?
you crush the electrons into the protons.
Is that a thing? That is a thing.
And then you
isn't
make
it?
neutrons.
That's how that works. Okay, right. So the proton, which is positively charged, and the electron, which is negatively charged, it kind of almost makes it sound like, well, a neutron is just a proton and an electron stuck together. It's not quite that simple, is it?
Not quite, but it's close.
It's close. There are weird quantum things going on in there. There's a completely different reaction going on, which involves a completely different force, and maybe we'll get into that another day. But you can have an interaction where a proton and electron combine together, and what pops out the other end of this interaction is a neutron. Right? The plus and the minus become a neutral thing.
Yep.
And that's what's happening.
That's what's happening.
Wow.
So instead of a big ball of electrons and protons and atoms and things that you used to have, you've now got a big ball of neutrons.
And that must be very heavy indeed, because we've gone from having atoms, and atoms are staggeringly mostly empty space. Right? If you are able to look inside an atom, and it's a bit hazier than this because quantum, but if you were to look inside an atom, actually the electrons are tiny, and the nucleus, the protons and the neutrons, they're tiny, and the rest is just sort of not, there's nothing
Space,
there.
yeah.
And now you're talking about, well, no, that atom structure is gone. The electrons have merged with the protons and made neutrons, and now there isn't the space anymore. And now you've just got basically a big lump of nuclear material, of neutrons. That's incredibly dense.
But we've got some really nice ways that we can imagine this.
Okay.
So for talking about a white dwarf star, that's already an incredibly dense object, right? So we're talking for a white dwarf, you're looking at something like the mass of the sun compressed down to something like the size of the Earth.
Mass of the sun down to the size of the Earth. And normally, like, the sun is how much bigger than the Earth? How many Earths could you fit in the sun?
You can fit 1,000 Earths across.
Right. So you've gone down by a very large amount. And just remind, so a white dwarf is what?
So that's the end result of a low mass star. It's kind of the core bits
Yeah.
that
But
are left over.
But what is in it? What's the, like, we're not at neutron star yet. So what is the core of a white dwarf?
So it's made up of the things that were left over from the fusion reactions.
Okay, so it's still
there's
atoms.
carbon, there's nitrogen,
Right.
oxygen, well, at least nuclei, and then maybe in a sea of electrons it gets a little bit.
Okay. So it's incredibly dense, but it's still just atoms. Interesting, but not new kinds of matter yet. You get past this Chandrasekhar limit, and now you're into something quite different.
Now you're into your ball of neutrons.
Yeah,
right?
okay.
And I say that as if they really is just a sphere made up of lots and lots of tiny neutrons. It's actually a lot more complicated than that. It's probably stuff that we don't even really understand in the core of a neutron star.
Well, it's complex stuff.
Yeah, we just don't have any other examples. Because if you want to imagine what a neutron star is, now you've got to take the mass of the sun and you've got to compress it down to the size of a small city.
So we had for a white dwarf, mass of the sun down to the size of the Earth. Now we've got mass of the sun down to the size of, say, London or something smaller.
Even smaller, 30 kilometres.
Good Lord, that's small.
That's really, really
incredibly
small.
dense.
Incredibly
Okay.
dense, yeah.
Mm-hmm. And what happens when you do that?
So you end up with this amazing, crazy object. Like, we have nothing like that we can reproduce on Earth in any kind of laboratory. The densities are so extreme. If you took a sugar cube of a neutron star, it's going to weigh more than 100 million tons.
Wow. Okay, that's off the chart. That's nuts.
I can't even imagine 100 million tons. Apparently, that's what all the population of the Earth would weigh if you put them all together.
Squeeze every one of the 7+ billion people and squeeze them down into a teaspoon, and that's what you've got. You've got a neutron star.
Yeah.
Yeah, and a big mess. Yeah.
And probably some very cross people.
But I mean, it kind of makes sense, right? That you think about an atom, and again, this is all very hazy quantum stuff. But if you think about an atom, it is, as they say, mostly empty space. And the bit in the middle, the nucleus, is tiny. But that's what we're talking about now. We're talking about the nuclear stuff. And if you make a star, a lump the size of a city, out of that material, you've gotten rid of all the emptiness. You've now just got that incredibly dense bit, which was the tiny little bit inside an atom. And now it's huge. That's got to be an interesting environment in space.
It's so exciting. They want the most exotic things that we have in the universe, really. Because they're very difficult to study. Now, of course, these things also have a limit.
Right.
Because neutron degeneracy pressure can only hold up a star for so long. And it's this limit that we're approaching with this story today.
Okay.
Now, it's not quite as simple as, I say simple, it definitely wasn't simple. The maths wasn't simple. That Chandrasekhar's limit, he was able to calculate it just based on theory. And it's been well observed in what we've seen in our local universe. But the limit for neutron stars is not quite as straightforward.
Okay.
Because we're now talking about states of matter that we don't understand. We actually don't understand very well at all what's inside a neutron star.
Yeah, I mean, the process that takes a proton and an electron and spits out a neutron, that was pretty weird 100 years ago, but it was understood not too long after that, and theories were developed, and we could see that going on around us. Like, that's something that happens in the world, right? It's a nuclear process. Going beyond that, beyond neutron degeneracy, can you squeeze neutrons together more and more and more? And eventually they get to a point where they say, no, we can't do that. But of course, no one told the star that. You can just get heavier and heavier. What happens beyond that? We're now getting into a realm where we don't see that around us in the world.
So we know there's a limit where you can tip over the limit and you become a black hole.
And as we all know, black holes are odd, weird, and not something that you see around you in everyday life.
No.
So studying them is difficult.
It's really difficult. And so we have some theories about how big basically a neutron star becomes before it becomes a black hole. And we do have some observations as well. And so far those theory and observations seem to be kind of matching.
When you say observations, you mean observations of things that we are pretty convinced are black holes in the universe, in the galaxy? Is that what you mean by observations?
Definitely, but also more complicated. So if you think back to LIGO, LIGO has observed the gravitational waves from two neutron stars merging. And using those calculations, we can also apply some constraints as to how big neutron stars can be. So the neutron star merger in 2017 suggests a limit of something like 2.17 times the mass of the sun, which is incredibly close and thankfully quite close to the theoretical limit, which is about 2.16.
Wow, okay. I thought you were going to say 2.9. It's not bad. No, that's quite close. Yeah.
So we seem to understand the majority, at least, of the physics that maybe are going into the basic structure of a neutron star.
Sure. Okay.
I don't want to go too far here because I know that a lot of people are working really hard and it gets really difficult.
Yeah, and we are right on the limits of, I don't know about you, Emily, but certainly my understanding of what the hell is going on when you get down to these levels. And not just our understanding here around the table in your office, but our understanding in the world.
Oh, definitely.
Of what's going on.
Yeah,
so this is complex stuff.
It is. It's very, very exciting because this is nowhere else in the universe do we find these objects. So they're really, really cool things to study.
And we don't make them down here on Earth.
Oh, no. Oh, no.
Tricky stuff. All right. So when did we... Okay, let's wind it back a bit. When did we discover actual neutron stars?
Well, we discovered them in the 60s because it turns out that neutron stars are basically a shared classification with another type of star that you might have heard of called a pulsar.
Right.
So a neutron star, if it was just this tiny ball of neutrons, it's not producing any light. It would be incredibly hard to see. We can't see something that's 30 kilometers across, from the other side of the galaxy.
That's ridiculous. We could never do that.
Not going to happen.
And if it's electrically neutral, then it's not going to be interacting with much. It's not spitting off any light. It's not going to be interacting with any light that comes past. Yeah. It's gone.
Yeah, right? You've just got gravity. So only very recently have we been able to see these things using gravitational waves.
But I'm willing to bet that it's never that simple, is it?
No, because these things turn out to be crazy, energetic balls as well that are spinning.
Right.
And part of the spinning means that they have actually a dipole axis of beamed radiation. Now, the clever thing about pulsars which is kind of the classification of neutron stars that have this beam. We haven't found any neutron stars that don't have a beam yet. So,
well, that kind of makes sense because the beam is the way you find them.
Yeah.
Right?
So maybe all neutron stars are pulsars. That's question mark. We don't know. But at least the ones that we observe are generally pulsars. So they have this beam, and we can see this beam spinning around, but like a lighthouse.
It's a beam of radiation. It's a beam of light, or if not visible, all sorts of different wavelengths of light.
Radio waves.
Right.
Yeah. So a great way you can think about this is this. I have a really cool dance that I invented, maybe, to teach my students about pulsars.
Damn shame this is just a podcast, not video.
No, but you can play along if wherever you're listening. Just make sure you've got about a little bit of space around you, so you can do this safely, guys. So what you want to do is take your arms and stick them out at an angle. So maybe stick one out at a diagonal angle to above your ears.
So one arm up.
And one arm going to parallel direction, going down.
Right. Okay. I feel like an aeroplane that's banking right now. Yep.
Yes, that's right.
Yep.
So now you are a pulsar, and your arms are the beams of radiation that are coming out from this pulsar.
Excellent. Good.
But now you've got to spin.
Oh.
So in terms of your axis...
I'm not sure we've got enough room in this office. I might break something.
In terms of your axis of spinning, you're going to spin around in a circle. Right. So shuffle your feet around, spin around in a circle. Dum, 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 dum. I can do it on my chair. Look. Whee!
Emily is now spinning around on her chair.
Being a pulsar.
Greater love and hath no astronomer. Love it. Okay.
Yeah, and all you got to do is do that something like 30 to several hundred times per second.
Easy. Right. And that's a pulsar. Okay. And so those beams, they're obviously clearly as you're rotating around... because you're not necessarily rotating along the same axis as the beams are coming out.
Exactly.
And so those are going to be sort of scanning in this cone across the sky in a way. And so the beams are going to sort of come past. And if they happen to be pointing at some point in the direction of the Earth, then we'll see that as a blip. And then another blip as it comes past on the next spin around, and another blip as it comes past on the next spin around. Right.
Yeah, just like a lighthouse has the turning lights that will blip around.
Right.
No matter where you are in the sea, you can see them.
This is what Jocelyn Bell Burnell found, wasn't it?
Yes, yeah. So she was looking for all sorts of different radio frequencies and found this incredibly regular signal from a very, very famous pulsar, which is in the Crab Nebula.
But we didn't know it was a pulsar at the time. And that was the weird thing, wasn't it? This is really regular. Yeah. Like, we don't see this in the sky. We see things that repeat, but this is nuts.
But these are regular, so regular that even at the time they were better than any atomic clocks that we had.
Wow. And atomic clocks are the good ones.
Yeah. That's right. Nowadays we can slightly beat a pulsar in terms of regularity, but only
they're
just.
Extraordinarily regular. Okay. Yeah. And so that was the weird thing at the time was, Jocelyn Bell at the time saying, well, look, I found this thing. I don't know if it's real or not. We've never seen one before. Just make a note of that in the margin. Are there any others? Can we find any others? What is this?
Definitely. Yeah. And she originally labelled the finding as LGM.
Right, which was?
Little Green Men.
Now,
it was definitely tongue-in-cheek.
Tongue-in-cheek there. Yeah. But, I mean, what else could it be, right? Is it aliens trying to contact us with this incredibly regular signal? No, turns out it's a spinning neutron star.
Yeah.
Could we just, where does the radiation come from? I mean, if this is a ball of neutrons, why is it spitting out
So they've got
radiation?
Insane magnetic fields.
And why do they have insane magnetic fields?
So because they're the remnant magnetic fields from the star itself.
Oh, okay. This is because of the collapse?
Yeah,
right?
Exactly. So a little bit like the conservation of angular momentum means that as you collapse down, you spin up faster. You also preserve a lot of your magnetic information as well. And so they have these kind of beams, which are charged particles that are zooming along these insanely strong magnetic fields. As those particles zoom along, they give off some radiation, some radio frequencies.
As we've gone from a big, normal, made of atoms type star, which is spinning, because they all always are. Nothing isn't spinning in the universe. It's always got something. As it collapses down, the angular momentum is conserved. And so as it gets smaller, really small, incredibly small, it spins really fast because it has to, because angular momentum, that's how that works. And what you're saying is it also hangs on to a large amount of its magnetic field. Some of it may be lost with some of the material it loses, I don't know. But it's got to conserve that magnetic field as well. And that becomes incredibly concentrated because it's now so small.
Exactly.
It's really collapsed down.
Yep.
Right. So you've got this very rapidly spinning, very small, very dense, very energetic, very magnetic ball of neutrons.
It's quite an extreme thing.
Yeah, that's not normal.
So you've got extremely quick rotation, which means that these things will spin, a standard pulsar will spin something like a few tens of times per second.
Okay.
So the Crab one, for example, I think it's 33 times per second.
And thinking about this, like these are things which are the size of a city?
Yeah.
Spinning that many times a second?
Yeah.
Okay.
That's really quick.
That's normal. That's
really
a standard common or garden variety pulsar. Yep.
But it makes them great things to observe. And we can observe now millisecond pulsars, which are pulsars that spin hundreds of times per second.
Wow. And is there any, I literally do not know this. Is there any relationship between size of pulsar and speed?
There is. Yeah, we think that the larger ones tend to spin faster and the younger ones tend to spin faster.
Okay. So that's our neutron star. The system that we've found is a neutron star and a white dwarf in a binary system. So tell us a bit about this one. Is this a common or garden variety? It's you said it's one of the biggest we've found.
Yeah, so it's definitely, we only know of something like 70 to 100 millisecond pulsars that we've found in the sky. So, it's part of a subgroup of nice pulsars. It's called PSR J0740 plus 6620.
That's even for astronomers, that's a shocking name.
It's a shocking name. PSR stands for pulsar.
Right.
The rest is kind of based on its coordinates.
Sure. Yeah. It deserves better than that. But anyway, move on.
Okay. So
tell me about this star.
Right. So this is a millisecond pulsar, and it pulses. You have to wait with me on this one. 346.531996493212 times per second.
Say that again.
346.531996493212 times per second.
That's just the number that you get out of the calculator when you do some maths. You're not supposed to take it to all those decimal places. That's what you learn in school. Only the significant figures, only the relevant decimal places. There's no way.
Except
seriously?
This is really important because we do know the accuracy to this level.
That's nuts. How many significant figures? That's like a 10.
It's an incredible measurement.
How do they know that?
Because we can observe it for a long period of time. So this observing...
And it's that regular.
It's that regular.
Wow. That's crazy.
And you sort of think, oh, well, you're showing off. You're just saying all the numbers that we know of. You could just round it and say, it's 340-something times
300
per second.
something.
Whatever.
Yeah.
But no, those decimal places matter because what we are talking about with these observations is changes in that period down to the level of a microsecond.
That's crazy. That's down to the level of a millionth of a second.
And
wow.
That's how we're measuring the mass of this pulsar.
Okay. So we've measured its rotation speed, its frequency. What else do we know?
So to go from measuring its rotation speed to getting how massive it is, it's kind of a multi-step process. So we can talk through the steps.
Yep.
So remember, this is a binary. Binary systems are wonderful. We can learn so much about them. We know the period of the binary system incredibly well because this is a wonderful binary system where the pulsar and the white dwarf basically eclipse each other.
That's rare because, it didn't have to be that way.
Definitely not.
At all.
They're just so aligned that every so often the pulsar comes in between us and the white dwarf, and every so often it goes behind the white dwarf.
And that's really handy because, as we've talked about transiting exoplanets before, and that's a really good way to find out lots of information about those exoplanets. Same thing here.
Exactly.
You can learn a lot about that binary system of stars. So how well do we know
The orbital period we know incredibly well as well. So we've measured that to be 4.766944691 days.
So, incredibly well being an underestimate.
Yeah, 4 and a bit days, right? Mm-hmm. Yeah. Okay. So that we can measure that in very, very well. Now, the wonderful thing is because this is an eclipsing system, guess what? It's a syzygy.
Yeah, good. Excellent.
An alignment of 3 celestial bodies, the
Well
Earth,
done.
the white dwarf, and the pulsar.
Well done.
Because we can measure this, when the neutron star goes behind the white dwarf, the signal has to travel through the gravitational field of the white dwarf to get to us.
Which is already very compact and dense, and so we'll have a very strong gravitational field.
Exactly.
Right.
So the white dwarf's gravity bends the pulse coming from the pulsar.
Okay.
Which means it delays the signal of the pulsar getting to us by 10 microseconds.
And so if you know the signal from the pulsar incredibly accurately, then that delay would be able to tell you what you'd be able to sort of work off the back of that incredibly accurate pulsar measurement to get what?
To get the mass of the white dwarf.
Okay. Yeah, I can see that.
Because you know the gravity of the white dwarf, then you can work out the mass.
So you can piggyback off how well you know the pulsar's frequency to get a really good estimate of, or really good measurement of the white dwarf's mass.
Yeah.
Okay.
And then the period of the orbit itself tells us the sum of the 2 masses in the system.
Oh, that's clever.
Yep.
That's clever. So you got the mass of the white dwarf really well from the pulsar, and then from the mass of the white dwarf and the orbital period of the binary system, you get the mass of the neutron star.
Yeah, so you just got to subtract you get the system mass, you subtract off the mass of the white dwarf, and you're left with the mass of the pulsar.
You astronomers are clever. Hey, well done, everyone. So what do we get?
So we get this answer of 2.14 times the mass of the sun.
I don't know. I'm almost disappointed by that. It's only 3 significant figures. I kind of feel like that's quite awesome. So 2.14.
Yeah, let's just remind ourselves that this is not only looking at crazy physics of the pulsar, crazy physics of the jet that's coming off of it. We've also got the crazy physics of gravitational bending. This is a relativistic
this
effect.
is general. This is Einstein.
It's called the Shapiro delay. There is so much really complicated physics.
Yes, I obviously am being facetious. Literally, well done, everyone. This is quite awesome.
So the final answer we don't get to 10 decimal places, but we can get it very, very confidently to 3.
And winding my memory back to earlier on in this episode, you said that the limit on sort of the upper limit of neutron stars was 2.1617, and we're at 2.14,
maybe even as high as 2.15,
which is to within what, a couple of percent.
Yeah.
So given sort of error bars and stuff on that, this is as big as you can get.
It's very, very close to the limit, and we think this might be the biggest one we've found. Of course, it's possible maybe we'll find a 2.16.
Sure.
But given the number of these pulsars that we know of,
because you said there were only, around 100 that we'd seen?
Yeah, around about 100 millisecond pulsars. So, the likelihood of us finding one that is bigger is fairly small at this point.
That's cool. That's very cool.
Yeah. And, okay, it's just, you say, well, you're at the limit. You're at a record.
Yeah, well done.
Yeah, that's amazing.
That's
and a wonderful set of physics to get there.
Well, not just a wonderful set of physics to get there, an amazing series of coincidences, right? Because a pulsar, as it's beaming its beam across the cosmos, doesn't have to be pointing at us, right? So we don't have to see that. So the fact that we are is good, right? The fact that it's in a binary system, so that we can actually make some measurements of its period and so on. That's handy. The fact that it's in an eclipsing binary, that's not a given. It didn't have to be that way. It could have been pointing orbiting in a completely different plane, and we wouldn't have had that data. And then the fact that it comes down to be 2.14 is extraordinary. Bunch of coincidences.
It is, and it's great. It's great to have such an object.
That must have been a great day to be an astronomer doing this stuff.
Definitely. So these observations were taken at the Green Bank Observatory, which is a 100-meter radio dish. Let me just say 100-meter radio dish.
Yeah, that's big.
That's a very, very large dish.
Green Bank where? In
the US.
In the US.
Yeah.
Yeah, that's big.
Yeah.
Is this one of those ones that's sort of buried in a hilltop somewhere, or is it actually on a pivot?
No, it's a steerable dish.
Wow.
Yeah, it's
that's
amazing.
huge.
Wonderful thing to look at. So this whole project is based around looking for gravitational wave signatures from these millisecond pulsars, and this was the first kind of result that they've had in their 12.5-year project working on this.
That's a long time to be waiting.
I'm not quite saying that right. It's not the first result, but it's one of the most exciting ones.
But it's a good one.
So far. Yeah,
it's a good one.
Definitely.
Okay, but all right. So given all of that, well done. Well done all. But
yeah.
Does that
So apart from sticking this little star in the Guinness Book of World Records,
well done and all of that. That's great. That's an interesting result. But so what?
What are we going to know?
Yeah.
Well, we don't understand the physics that are going on in the interiors of these stars very well. There's something called an equation of state, which is basically an equation that describes how things like temperature and pressure are related to one another inside an object. We can calculate equations of state for lots of different things, and they work very, very well. Gas pressure. I mean, there's a very famous equation you might have seen at school, which is pressure times volume equals nRT. So number of Rydberg. Oh gosh. Okay, I'm going to skip
V equals
this
nRT.
one.
It's pressure volume equals measure of number of atoms or molecules.
N and R are constants.
R is a constant, and T is the temperature. So it's relating pressure, volume, and temperature to the type of gas. And so on. Yeah.
So that's an example of equation of state. That's kind of
It's a way of characterizing a whole bunch of things stuck together in a space. How can we understand this? What's going on?
Yeah. So but of course, inside a neutron star, everything changes.
Yep, all bets are off.
So trying to find out what the equation of state is of a neutron star is a really big active area of research, because this is such a weird environment, and there's new physics probably going on inside there that we don't know about yet.
We haven't had to throw out all physics. Like, physics still applies, and then there's some really good theories still should be applying at that point. We haven't thrown out all the rule books, but at the same time, it's not a kind of physics that we can easily experiment on here on Earth. So to really understand what's going on there, you've got to be very, very clever.
Yeah. And there's a lot of really exotic nuclei and particles that we can theorize to exist, but making measurements of objects like this can put real constraints on those. So we can already rule out some different types of particles and nuclei that don't exist because we've made this measurement.
So looking at these bizarre objects out there in the universe, actually we can turn the tables, and rather than using the physics that we know to understand the object, we can use measurements of the object to try to understand the physics a bit better.
Exactly. Yep.
Clever.
And then we can go to look at black holes, of course.
Because, that's the next stage, isn't it? Is that once you get beyond the various limits, what happens next?
Yeah. So this puts, again, real constraints on the minimum sizes of black holes compared to the maximum sizes of neutron stars.
Right. Yes. When does that transition happen? Can you if you were to turn around and find a neutron star which was 2.3 times solar mass, and you go, well, that shouldn't be possible. But we're not seeing those. We're seeing one very, very close to our theoretical limit, and studying that limit is really important for trying to figure out all sorts of things.
It is. And you can even pull this back to looking at the evolution of stars in general. So it's really a part of our biggest pictures of the universe. So we have the universe around us. Stars are kind of the fundamental building blocks of the universe, right? You need stars to make a galaxy. You need stars to have planets that go around them. They're kind of like the core ingredient one must have for all the things inside the universe.
Thumbs up for stars.
Bread and butter. Yeah. I mean, we can forget sometimes how important stars are when we talk about, all these wonderful other things that we have. But yeah, they really are the core fundamental physics of the universe. So understanding how a star is born, how it progresses through its lifetime, and how it evolves beyond the time it can fuse is really important to understanding, of course, stars, but also planets and the development of planets. But then going bigger again, we can go back to galaxies. How do galaxies evolve? And then, how galaxies evolve affects how the whole universe evolves. So they're just so important to get.
Well, we're going to have to call it quits there on this Neutron Star-tastic episode of the Syzygy podcast. Emily, I thought I knew a fair amount about neutron stars, and now I kind of feel like my world's just been opened wide up. My brain is now full.
I think we're all basically at the limit of our understanding now.
Yeah, that happens a lot to me in this podcast, actually, which is really nice. Listen, if you have enjoyed this episode and you want to get in touch and say hi, throw us a question, throw us a comment, just for any reason whatsoever, there are a bunch of different ways that you can do that. You can go to our website. Emily, what's our website?
We are at Syzygy FM.
We are.
So SYZYGY.FM.
Yes, that word which is always so good for Scrabble. And at our website, you can find all of our past episodes, all the show notes, all the images, all of that stuff, as well as a contact form where you can go and send us a little message and say, hi, got this question. In the past, we've had questions which we've dedicated entire shows to. So get in touch and let us know what you want to know. How else can people find us?
Well, if you've taken an amazing selfie of you doing a pulsar dance.
Oh, yeah.
Then you should definitely tweet us, Instagram us, Facebook us. We're on all of those things at Syzygy Pod. Google Syzygy. You'll find us in all of your favourite social media.
Yeah, if you do that, definite 100% shout out on the next show. Absolutely. I would like that a lot. Please do. Yeah, at Syzygy Pod, pretty much anywhere out on the interwebs, really. People can find us. Before we go, there is one thing that we need to do, which is to say hi to our brand new Patreon patron signing up just this week to help financially support the show. I'd like to say big, huge, cosmic-sized thank you to Rob Bartell. Thanks very much, Rob.
Thank you.
Great to have you on board. But otherwise, that pretty much brings us to the end of the show. So we're going to be back again in a week or so. We're trying to get back into this regular recording routine as we come out of summer. It's getting darker here in the UK.
Yeah, is it actually daytime, Chris?
I'm not entirely sure. All I know that it is definitely wet. So we will join you again in a week's time for more cosmic goodness. See you later, Emily.
See you later.
Bye, everybody.